Welcome to the Quantum Map, Unveiling Atomic Orbitals. We will explore the idea of the atomic orbital, a three-dimensional region where an electron is most likely to be found. This concept is central to modern chemistry and physics, defining how atoms bond, react, and build the world around us. The shift from fixed orbits to orbitals relies on the Heisenberg uncertainty principle. Electrons behave as probability waves, and their location is described by a probability density. This address is defined by the four quantum numbers: principal N, angular momentum L, magnetic Ml, and spin Ms. The principal quantum number N describes an electron's energy and distance from the nucleus. It is a positive integer, 1, 2, 3, etc., defining the electron shell and the maximum number of electrons a shell can hold, given by 2n squared. Higher n means larger orbitals and higher energy. The angular momentum quantum number L determines the orbital shape. It ranges from 0 to n1. L equals 0 gives the spherical s orbital. L equals 1, the dumbbell p orbital. L equals 2, the cloverleaf d orbital. And L equals 3, the complex f orbital. The value of L also dictates the number of angular nodes. The magnetic quantum number Ml specifies the orientation of an orbital in 3D space, taking integer values from -L to +L. This gives 2L plus 1 possible orientations. For a subshell, all orbitals are degenerate. The Zeeman effect confirms this quantization of angular momentum. The spin quantum number Ms describes the electron's intrinsic spin, which is a purely quantum mechanical property. An electron can only have two spin states, +1/2, spin up, or -1/2, spin down. This is critical for the Pauli exclusion principle and Hund's rule of maximum multiplicity. The s orbital is the simplest and most symmetric, with L equals 0 and a spherical shape. Its electron density is highest at the nucleus. S orbitals are present in all shells, form strong sigma bonds, and exhibit maximum penetration toward the nucleus. The p orbitals, L equals 1, have a dumbbell shape, consisting of two lobes separated by a nodal plane. They appear at n equals 2 and have three orientations: px, py, and pz, aligned along the Cartesian axes. Their directional nature is crucial for forming both sigma and pi bonds. The d orbitals, L equals 2, exhibit complex geometry and first appear at n equals 3. There are 5 distinct d orbitals. 4 have a cloverleaf shape, and 1, dz squared, has a unique dumbbell and torus shape. Their nodal structure is complex, and their energy splitting is key to transition metal chemistry. In conclusion, the 4 quantum numbers provide a rigorous coordinate system for every electron, defining its energy, shape, orientation, and spin. This quantum architecture governs orbital shapes and bonding, explains the periodic table structure, and predicts chemical behavior, forming the foundation of materials science.